will be all about the different kinds of measurements that exist in science, physics, and specifics. In case you were, it's the title of the lesson, there's two different types. There's scalars and there's vectors. And they have to be different because how we combine them together is different math. And so that's what we'll get through today. Certain measurements we use are scalars and certain measurements we use are vectors. I'll get into what that means as part of this lesson. But being able to work with both of these and being able to identify each type based on the context is important. So what we're going to do is we're going to start with a scalar quantity has only a magnitude. Only, oops, I don't want it red. Only a magnitude. Now that's a pretty fancy word. So I'll also just put like on the side here, size. Like it has only a size. It doesn't care what direction it's going. So that's the word here, direction. So it doesn't care what direction. And it can be a positive or a negative number. And it has to have an appropriate sign, which signs means like pluses, minuses. That's what that means when I say sign of a number. The way scalars can be positives and negatives is because whether a number is positive or negative in a scalar depends entirely on its reference point. So some examples of scalar quantities are, and my first example will be temperature. Now I'm going to use temperature right here because it's a good example of how positives and negatives work with scalars. In our common usage, we use Celsius here, and that can have positives and negative numbers. But that's only relative to the freezing point of water, where we have 0 as the freezing point of water, so negative numbers are common. If we use a different temperature scale, the Kelvin temperature scale has 0 set to absolute 0. You cannot have a negative number, so that doesn't make sense. So all the temperatures measured in Kelvin are positive and negative, are all positives. And so while temperature itself is a scalar, depending on where you set 0 to be, you can have positives and negative numbers. So yeah, height works, like sea level, because it can go above and down, that's fine. So I'm going to call it height to be specific. Height is a scalar. Like how tall I am doesn't have a direction, it's just like from my feet to my head. So that's just, that's fine. Other ones, any other suggestions? One of the checks I like to do is it doesn't have a direction. So saying something like mass is also a scalar, that measurement for mass. If I say a direction after this measurement, would it sound stupid? Like I wouldn't say there's an 80 kilogram up. It's like, what does that mean? Or like 17 pounds left. It's like, well, that doesn't mean anything, right? So these kinds of things, if you can't put a direction after that word, it's a scalar. If that will sound dumb, it's probably a scalar. Another one that's probably the most common one we will deal with is time. Time is a scalar. Time moves forward constantly, and it can't do anything but that. There's some other ones. I like this one. This one is luminosity, or how bright something is. So it's not something we're going to use very often, but it's a nice, fun scalar. The last thing, the rules of scalars are ordinary math. Normally that will cause some concerns. Why did I bother saying the rules are ordinary math? That's because the rules of vector are not ordinary math. Special. And so we'll worry about that in our next chunk. So that's all the scalar talk. Now we talk like the other kind, which are vectors. So vector quantities require specification of both a magnitude, or like size measurement, and a direction. I'm going to write it here like this, and, because you need both, direction. So these are measurements of some quantity that requires direction to be included. It must have a direction. It can't exist without direction. So probably the most common one that we will deal with all the time is a velocity. It's like it's how fast are you going, and when you're going somewhere, you have to be going somewhere in some direction. And so when you're measuring a velocity, you had to go somewhere, so that direction is necessary to include. Along with that, there is acceleration, which is how fast you change speed. We'll get to all these like actual physical descriptions in lessons down the road. But for us, all we care about right now is that they are vectors. Any other suggestions on what could be a vector? Two other ones that we're actually going to use quite a lot are force. Forces have to go in a direction. If you're pushing or pulling on something, they have to go somewhere. And then the most important one here, I'm going to put even in fancy ones, it's a displacement. Oh, I put it in a different color for a reason, because it's a super important one. Because displacement is how far you have gone from a point. So it's like you go from a point to another point, your displacement. It's your change from some starting point. What would I measure that in? What kind of units would I measure a displacement in? Any guesses? How far I get from a starting point? Was probably a length measurement of meters, right? I would travel a certain number of meters away, or if it's really far, kilometers, or if it's really, really small, millimeters. But it's all displacement. Is there any scalar up on your list that you would also measure in meters? Height. So height and displacement really are like similar. What's different about them is context. So a height is a static distance traveled, or like the direction has no point to the context of the question. So a lot of these, whether they're scalars or not, will be context specific. And so height is one of those things where the direction doesn't matter, but a displacement, a position change, a distance traveled, like from somewhere to somewhere, that direction that you went will matter. So when it's directions, you need to have a vector. So when direction matters, vector matters. I just wanted to put that in like the beginning of this lesson. There are two main ways to do the math on this. There is graphically, which sounds hard, but it's not actually. Graphically, spelling it right. And component. Graphically sounds really fun, but it's basically just arrows. So we draw arrows to show where things went. It went from here to here, and we just like draw them, and then when we put them together, we just draw more and more arrows, and we can see where all the arrows end up. So while possibly tedious if it's long and you got to get some rulers out and protractors to get angles right, it works. Component method is the one I'm going to show you how to do later in this lesson. It involves math. So we're going to do a lot of math. I mean, the graphical one also involves math, but you can do it with like measurement tools, and component ones we're going to do entirely through math and trigonometry. Yeah. Okay, vectors have some properties which is super useful for us to work with them. A vector is represented by an arrow. I know I just said that out loud, but it's an arrow. And that means its direction. And a length, its magnitude. So while you will be drawing some vectors, we won't be drawing vectors with like precision. We won't be getting our rulers out, measuring to the millimeter and drawing them that way. What I expect from your vector arrows is them to be what we call proportional. Whereas if one vector is about twice as big as another vector, that arrow should be about as twice as long, like it should be longer. If you draw vectors that have different sizes, all with the same sized arrows, it will lead you to wrong results. Now, whether we're not measuring them, it will trick you into thinking your math is wrong if you drew your picture wrong. Vectors are equal if they have the same magnitude and same direction. A vector can be translated parallel to itself without affecting the vector. Basically what that means is this is translation in a mathematical sense. Do you guys know what a mathematical translation is? No. Mathematical translations are just sliding an image around the graph. So if you take like a triangle that you've drawn on like a grid paper and then just like shifted it to the left, that's called a translation mathematically. It didn't grow, it didn't spin, it just shifted like parallel to where it was. So it's the same shape, it just moved where it was. That's called a mathematical translation. And so anytime you translate a vector, it stays the same vector. You can move them around without changing what that vector is. To be boring, I'm going to draw a vector that looks like this. It's very exciting. I'm going to call it very, very creatively vector 1. I'm going to draw another vector, and I'm going to say it's this vector here. These two things are equal. Vector 1 and vector 2 are equal because it's the same length, as accurately as I can draw it, and it's going in the same direction, as accurately as a drawing on an iPad can be. I haven't changed its length, and I haven't changed its direction. But if I change its direction, like I do, like say this one, but it's roughly the same length, and I call this one V3, then these are not equal now. Because now I've changed its direction. And if I keep the same direction, but make it like really short, this little V4 here, it doesn't matter really where you put it, these are not equal because while it was in the same direction as the first two, I know I've got it really low on the page here, it's not the same size. It's way shorter, so it's not the same vector. But you would probably be able to tell that. The direction one might be less obvious, but the size one would be like obvious. It's like, this is 2 centimeters and this is 5 centimeters. Are they the same? No. Right? You know that. All right. Magnitude of every vector is positive. And this is because it has a length, right? When you measure how big something is and you got your ruler out, it's going to have a positive number. A negative number for like a length of something doesn't have a lot of meaning to it. And so magnitude of every vector is positive. The negative of a vector would have the same magnitude, but a different direction. In this case, opposite in direction. So if you want to do a subtraction vector, you got to take a vector away. You just add the opposite one. So like if I put a vector that looks kind of like this, and then a vector that kind of looks like this is negative V1 in this case. So it's the same vector, but if I change the direction to exactly opposite, it's the opposite, the negative of that vector. Oops. Didn't even finish writing the word direction yet. There, now I finished writing it. So that's how we do opposites. So if we want to do a subtraction, we just do, addition of a negative. When we add vectors, we essentially always add vectors. If two vectors are contributing to the motion or effect of a certain object, we add those two things. If we're trying to find something in the middle, then we're doing like a solve, and that might involve a subtraction operation. But when two things are like combining, that's adding. And just like regular addition, it's independent of order. Independent of order. There's a fancy mathematical name for that I like because it's silly, but it's not important at all. So independent of order is something called commutative. That's not important to anything, except stupid trivia. And that's basically shown here. I didn't bother making you guys write this, but if you add v1 plus v2, that's exactly the same as adding v2 plus v1. Just like regular numbers, the order they go in doesn't matter. And you can group them in brackets however you want. That doesn't change any of the math when doing addition. Let's do a few things here. So that's it for like the description of what vectors are. We're just going to do a few descriptions here. This shouldn't take too long. It says problems down below. You should be able to just blast through these as I slide this up. So basically all I want you to tell me is like, is it a scalar or is it a vector? See if you have internalized these rules. Some of them are going to be easy, some of them are going to be hard. So just write down scalar or vector for each of those. Take a second. All right, there should be enough time to just write down the scalar vectors. If you happen to be wrong, just cross it out and change it. Time. That's boringly a scalar. It's always a scalar. It can't be. There's not a lot of scalar. There's nothing that's too much. So just the time. It doesn't have a direction. The average speed of the student while running. Scalar, speed. The average velocity of the student while running. Vector. So this is where it gets a little tricky. So this is one of those things that speed and velocity are different. So this is my favorite thing to do in physics class, and your least favorite thing in physics class. In English, words are the same. Some words are like, that's the same thing. If you said the velocity of something and you said the speed of something, those are the same things in most people's vocabulary. For us, those are two different measurements. In this case, the speed is a scalar and the velocity is a vector. The way I like to remember about this is, how does your car tell how fast it's going? How do you know how fast your car is going on, Alex? No, it's not usually how fast it's going. It's how fast your engine's going. How fast is your car going? How do you know? The speedometer. Does your speedometer tell you what direction you're going? No, it does not. It only cares about the magnitude of that number. So it does not care what direction it's going. So speed doesn't care what direction it's going. Velocity does care. So this is our first introduction to two words in physics class that kind of mean the same thing, but are distinctly and precisely different. We will get to a ton of them. And even, is there more next year? I don't remember. There's a lot this year, and we get to do them over and over again. Displacement, I already told you that's a vector. Its scalar component is a distance. So, again, you would probably say distance and displacement are the same word, but they are different in physics class. A distance traveled is a scalar. It just cares how far, just like steps taken, how many laps, it doesn't matter. A vector measurement is a displacement, how far from a starting point this like distance was. You have two different changes in position, I would call it. So those are those two. In a certain city, the temperature is 23 degrees at one time of the year and negative 23 degrees at another time of the year. That city is not here because it doesn't get to negative 23 ever. But I've definitely had cities that are significantly lower than that. Do the plus and minus signs imply that the temperature is a vector? No, it doesn't, right? What are the positives and negative signs implying? No. Basically, it's the temperature. Temperature is above or below a reference. Like we say the temperature is like up, but the temperature isn't up. The temperature is increasing, but the temperature isn't going up. Like it's not physically going in an upward above the ground direction, right? And when the temperature is falling, it's not actually falling. The number is decreasing, right? We're using these, phrasing of them because the physical thermometer, the little liquid, is going up or the liquid is going down. That's actually the vector. The vector is that liquid's position is changing. It went from an up position to a down position. It changed positions. That change could be argued is a vector, right? The distance between the beginning temperature reading and the end temperature reading can be a vector. But the temperature didn't go up or down. The temperature increased or decreased. So that's why I like to include this part of the question. So the temperature is above or below a reference point. I think minus 23 is definitely negative in Fahrenheit still. But that's one that negatives and positives don't necessarily imply direction. All right, let's take a look at the next one, which I think is really fun because I get to show two things. We get to really hint at our second unit, which is all about forces. We're not going to worry about too much about the nature of what force is. We just know that it is a vector. That's all we care about right now is force is a vector, and that's all that matters for us now. So a student is pushing with 320 newtons of force on his car, trying to move it eastward. The force vector, which we like to write as force, and we can write it with an arrow going towards the east, and that arrow can be 320 newtons of force. We'll worry about what that actually means later. And we can say that he's pushing on this object. This is how we draw objects in physics class. We don't need to get our shading pencils out. We draw simple geometric shapes when we're doing physics diagrams, squares, circles, triangles, arrows. Simple geometry. I don't want to see any perspective relief drawings of cars while doing physics questions. It's not worth your time. And it's generally just going to be more confusing and details might get lost. So this is the push on the car in this case. So basically we're trying to think of what would the negative of this vector mean? What would the physical reality of the negative of this vector mean? Go ahead, Howard.
Would just be the same force pushing in the opposite direction.
Right, but what's pushing?
I don't know, another student.
Okay, it could be another student pushing back, but is there another student pushing back? There's no mention of it. It's possible, but it's not really what we care about here. Alex?
Would it be if you're pulling it?
Well, you could be pulling it. There's no indication that the car is being pulled either. What would a vector that looks like this, right? This would be negative f, and that negative f is also has to be exactly 320 newtons because it's the exact opposite. The negative of vector also has exactly the same magnitude because it's the negative. It can't just be another one. It could be a different force, but in this case, the negative vector. Now, this is also going to chalk up to you have no idea if 320 newtons is a lot of force or a little force. Turns out, not much. It's not none, but as far as a car is concerned, it's very little. 320 newtons of force is very little. So if this student is pushing at 300 newtons on his car, the car is not moving. It's not going anywhere. So in this case, physically, I would probably call the car resists. Resists. The car resists the motion. You push on a car lightly, it's not going to do anything. Basically, it has the effect of pushing back. We'll get into, this is one of Newton's laws of motion. we'll get into what that means physically, all in a much later chapter. But this is just like reminding us that this force vector and its negative are exactly the same size and in exactly an opposite direction. So it's kind of akin to is if I lean on the wall. Am I pushing on the wall? Yeah. Is it going anywhere? No. So the wall has to be pushing back with exactly the force I'm pushing on it. If it was less than that, it would go somewhere. Like when I pick up my cup, I put force into it and it moved. So it didn't push back with much force. Or it pushed back with less force than I gave it, at least. Measurement-wise, we don't care. That's it. We're going to now add these vectors using trigonometry. This is called the component method, and it's basically the only method I'm going to teach you how to do. There are graphic methods. There are methods involving sine law and cosine law. If you know what those are, cool. But if you don't, doesn't matter. The sine, cos, and tan you used in 10th grade math are not sine law and cosine law. That's different. When you learned SOHCAHTOA in 10th grade math, that's not sine law and cosine law. Those are separate things related to triangles, but different. We won't be using them in this class. If you know them, they do technically work, so they're not like unallowed, but they're not like part of it. Okay, so we can take any vector at any angle and take it apart into a horizontal and vertical component. Horizontal and vertical. So basically, horizontal and vertical. We take any line on a graph and say, this is some x and some y. Horizontal, in case we forgot, that's the x one. And the vertical one is the y component. So anytime we take anything vertical, vertical we're going to call y, and horizontal we're going to call x. I have to use my arms or I'm going to say the letters wrong. So a little example of a vector. I'm just going to draw on the little margin here. I'm going to draw a little simple axes here and draw a big vector on it. Very exciting. So my red line here is my vector. I'm going to call it creatively V for vector. The top of it is a y. The bottom of it is an x. And so we can say a few things about these two things. We can say how far up it goes. We can call that the vector in the y component. How far up it went. And we can also measure how far across it goes as the vector's x component. So those are the two things we can write there. Let's leave that nice and high on the screen. So those are the two pieces of it. Now, to relate how much x and how much y, we also need to introduce our angle in this. So we're using our circle with a line through it, known as the letter theta. That denotes angle. Could the angle be equally here? The answer is yeah. But in physics class, I implore you, always, always, always put the angle from the x-axis up. So just always put the angle here, we measure it to the horizontal. If you're doing about physical things, if I wanted to see how tipped up this piece of paper is, should I measure it from the vertical down or should I measure it from the table up? Table up will make much more sense physically, be much easier than some imaginary straight up and down line it's measured to. So in a realistic measurement way, from the horizontal or ground up makes more sense, and also mathematically makes more sense. Those of you who are experts in math know what reference angles are. They are always measured from the x-axis. Your calculator will always give you a sine, cos, or tangent measurement from the x-axis or its reference angle. So if we're all consistent going from horizontals everything is fine. If there ever is a question that starts giving you angles from your vertical, stop and go, I'm going to translate that angle, do the math on it, move the angle over to the horizontal, and then do anything I'm going from there. Okay, next thing I'm doing. Oh, the two components are always perpendicular. Perpendicular. And that's, we call them Vx and Vy, and they're parallel to those axes. Okay, so let's see how much you remember. So, if I want to use the x component and the main vector component, which of those fancy trig ratios should I use to incorporate this part of the triangle and this part of the triangle? How much do you remember of your grade 10 trigonometry? So let me just slide over here, see how much room you have on the side. And remember how triangles work. So I'm going to draw a little triangle over here. I'm going to draw the angle here. And remember the different sides. Remember the long side of the triangle? It's called a hypotenuse. What is this side of the triangle called? It's called opposite, which is boringly labeled OPP. And then the other side is called, there we go, we remembered our grade 10 trigonometry. I didn't remember how to spell. ADJ is how we usually write adjacent. So, we also need to remember our fancy trig ratios. We have this as well. That's it. We remember what these mean. Everyone's just like, I know. It's like, oh yeah, I thought I could let that go. No, we can't let that go. So let's SOHCAHTOA there. So, for the x component, I am using I want this piece, which is the hypotenuse, and the x component is down here. So which of those do I want? That one, right? I want the CAH. So that's my cosine rule. So we're going to get back into here and do, the x component is based on the cosine ratio. And the cosine ratio is the adjacent side, the x component, and over the v component. So if I rearrange this, v to the x is equal to the original vector multiplied by its cosine of the angle that it has with the x-axis. Oh, there's a lot of words to say that you just take the cosine of the angle and times by the original vector size, and you get how big the x vector is. The y component is exactly the same, but with a different ratio. Which ratio should we use for the y component? It's not that one. We've used that one. It's this one or this one. We use sine. We use sine. I was really hoping for an enthusiastic response there. We get sine of the angle is equal to Vy over V, so that the y component is going to be the original vector multiplied by the sine of the angle. Awesome. That's that. What's next? Oh, that's the end of this page. Cool. Yeah, that's the end of this page, right? If I remember what I'm doing here. Cool. Sorry. These are the steps we're going to use for all the adding of vectors. They're the same every time. So as much as this method might feel a little tedious, it always works, and it always works. And you always do the same, I like to say 4 things each time. I'm going to show you what those are now. So we're going to take 2 vectors here. I'm going to draw a few of them. So I'm going to take this little side here and draw it like this. And I'm going to have 2 different vectors here. I'm going to take a kind of flat-looking vector, and I'm going to take a up-looking vector. And we're going to add these 2 vectors together. Let me just make these a little prettier. So if I add this first vector to the second vector, I get this what we call resultant vector, which is basically the difference between the beginning and the starting point. So we call this vector here with an R for the resultant or additive property of all of them. And I'm going to boringly call this one vector 1 and this one vector 2. Very exciting, right? Creative names all around. So what we're going to do is we're going to look at each of the components of each of the two vectors in time. So I'm going to draw those in here. So I'm going to draw a retranslation of vector 1. Well, it's not a great job of vector 1. It's a little flatter than that. So let me do that one, but a little flatter. That's fine. And this vector 1, has an x component and a y component. It has v1 in the x direction, and it has v1 in the y direction. So it has both of those things in it. Now we can add this to the second vector, which will look like this. I'm going to draw it nice and steep so they look different. And it also has, an x component and a y component called v2 in the x direction and v2 in the y direction. So this is our subscript going nuts. So far, there's only 2 subscripts. We get some in Physics 12. They get 3 subscripts, which is getting really out of hand. But that's our 2 vectors. So we can add these 2 vectors together to get our resultant vector after. Now, this does look really, really fancy and complicated, but it's honestly a lot easier than it looks. So, looking at part B here, I didn't even write the first step. What's the first part? Oh, yes, and it's important to take positive and negative. Oh, geez, that's terrible. Positive and negative direction into effect. In this case, I have chosen an example, all positive numbers. All positive numbers. I haven't done any negatives yet. Nice and easy, all positives. So we're going to find the algebraic sum, or regular sum. Algebraic is a fancy word for just normal, of the x components, and this is the x component of the resultant. So the way I like to write this is just Vx is equal to Vx1 plus Vx2. So basically what this means is I'm taking this size and I'm adding it to this size. So get how far, in this case to the right, I've gone. I will get how far from here all the way to there if I take the V1 part and then I add the V2 part. I just add those 2 sides together. Exactly the same thing for the y direction. We're going to take the sum of all the y components and get the y component resultant. And that's going to be Vy equals Vy1 plus Vy2. So just add the 2 ups together. Both. Resultant. That's just my bad spelling. Thank you. It's in result and then ant. Yeah. My bad spelling. Too excited. On using these x and y components, these things I just found right here, and my favorite thing in all of triangles, where we are here, Pythagoras. We can get the magnitude of the resultant vector. So we can take our total Vx and our total Vy and do some Pythagoras on them. Slide up and do this. And get our resultant vector. So the resultant vector, oops, that's not what I want to write. I want to write big V with an R is equal to square root of Vx squared plus Vy squared. So we're using Pythagoras' theorem to solve for the long side of this triangle. It will look like This, oops, undo, like this, like that, like that. And so this is going to be VR, VX, VY. Right, so we're just doing our Pythagoras here. And this is a right triangle. Because it's X's and Y's. X's and Y's have to be at right angles to each other. Otherwise, they're not the X and Y axes. The next thing we're going to do is the inverse. I think I'm just going to start powering through this because I think it'll make more sense once we try one. Inverse, which looks like this if you're using your calculators. The inverse trig functions to determine the angle. Which specifies the direction of the vector. Because this is a resultant vector, it has to have a magnitude, a size, and a direction somewhere to go. So we have to be able to find how big this is and in what direction it's going. So here we have the size and the inverse direction we use. So if I want to use these two sides of a triangle, which ratio am I going to use? We're going to use tangent. So the tan of the angle equals Vy divided by Vx. So the angle itself equals tan minus 1 Vy divided by Vx. So in this particular case, why does the Vy go on the top of the fraction? Why doesn't Vx go on the top of the fraction? Draw this example. So a student is going to run 120 meters in a direction 30 degrees east of this particular, of north, and then 86 meters in a direction 20 degrees south of east. So those are the things. So first step is to draw a diagram of what's happening here to be able to do the math on these two vectors. So we basically want to figure out where is the student even at this point. They ran 120 meters, 30 degrees east of north, and then 86 meters in the direction east of south. How far away and in what direction are they from their starting point? So I'm going to draw you a little one here, but I'm going to cheat because I know what the answer is going to be. So I'm going to draw it here, and then I'm going to draw the other one kind of like this. So normally you would draw your compass as a much more straightforward north, south, west is on this side, east is on this side. But I know everything is going to be over in this quadrant, so I just drew it because I knew it would all be over there, otherwise I have a lot of wasted space. So what we're going to do is we're going to draw the first vector. It's going to go 30 degrees east of north. So that's going to go kind of in this direction like that. And the way we do the second one is we kind of do a sneaky, like, reset here. You kind of go, okay, now that I've ended up here, where's my next direction going to go? I'm going to go 86 meters in a direction 20 degrees south of east. So I'm going east, but 20 degrees south of it. So I'm going to go somewhere over here, like that. Yeah, it's not bad. And so my resultant vector here, the one I have to solve for, is this line here. So what I need to find is how long is this line and in what direction is that line going. So I have one problem at the very beginning of this setup, and that is 30 degrees east of north. That puts the 30 degrees east of north right here. That's where the 30 degrees is. It's between the north side and that purpley pinky line there. That's bad, right? Why is that bad? Well, it's not good. It's not necessarily wrong, but it's not what we want. How do we turn it into something we want? Because that angle is measured to what axes? Y, right? We don't want Y angles. They're bad. We want the x angle. So what is the equivalent one all the way there? How big is that angle? It'll be 60. So that's 60 degrees here. So much better. We're going to use 60 for all of it. So as much as that's there, and I want you guys to see that it's here, I'm going to take this moment right here and go, no more with that 30. We're not going to use it anymore. Don't put it into your math questions. That 30 was how we got the 60, but now I want to do a little cross in it because don't put that into any of the trig ratios. I don't want you to find the sine or cosine of 30 degrees. I want you to do the sine and cosine of 60 degrees. We got to figure out where's the other angle. The 20 degrees, where does that go? Does the 20 degrees go here, or here, or here, or over here? Where does that 20 degrees go? Yeah.
Wait, I think I'm wrong.
No, it's okay if you think you're wrong. I would appreciate an answer.
Okay. I think it would go from the bottom line of that compass you draw
Yeah.
in between the two lines.
Yeah, it's going to go, I think you're trying to say here. Is that what you're saying?
Almost.
Oh.
That is right.
But this is the correct way. So everyone was going to copy down what I did. So I was just going to assume you were right. 20 goes there, which is fine. And that's where it should go. Okay, so that's there. I think I can get this next part done. So for the next part, basically now that we've drawn this thing appropriately and all the correct angles are in, we can now set up finding each of my components. This is the worst part about this one, and it's finding all of the components. So the first one is going to be V1 in the x direction. So I want to find out basically how far to the east in this case did the first vector go? How much east did the first vector go? Basically this distance here. Between here and here, that works too. So what we're going to do is we're going to use the formula that we did on the very first part of this, and that's going to be V1 times the cosine of angle 1. And so what we're doing for V1 is like, how long is V1 in this case? The first vector distance was 120 meters. So the first number is 120, and we're going to multiply it by the cosine of the first angle. And the first angle that we actually care about is 60. So that's the first math step we're going to do. We're going to do 120 times the cosine of 60 degrees. Now this actually works out really nicely. This is 60 meters. Probably a good time to check your calculators. Notice that I'm taking the cosine of 60 degrees. Make sure your calculator says degrees on it and not radians or some other silly thing. Has to say degrees on it. Physics class, we use degrees. Any poor saps taking Math 12 right now? Nobody doing PC 12? Oh man, PC 12 teaches you how to do angles in radians. That will make sure your calculator is the right for both of them. If you do your math test in degrees, they'll be bad. If you do your physics test in radians, they'll be mad. You got to really check on that every time you start doing these. So 60 meters is good. It'll be harder for math class because in physics class we get context. 60 meters is a perfectly reasonable number here. In math, it'll be less obvious when the number's silly. Next one, very the same. What we're going to do is we're going to do V2x next before the bell rings in 2 minutes. We're going to maybe stop there. So we're going to go V2 in the x direction. So that's going to be V2 cosine of angle 2. Oops, that's not, I don't want Q, I want theta. Theta 2. So in our case, the second length is 86, and it's still cosine, but the angle is 20. So now we're going to try this in your calculator. It's a little less obvious. We're going to get an ugly decimal because it's a less nice angle. I think it should be 80.8 meters. So if we get that in our calculator, we're successful, and that's where I think I'm going to take a deep breath and hold it for the second part. All right, so for doing the sine ratios of like this, the y components, we're using sine. They're interchangeable in my vocabulary. We're going to do V1 in the y direction will be V1 sine of the angle 1. I keep trying to write Q by accident. And it's going to be 120 times the sine of 60 degrees. And I'm going to write in, while you guys are calculating, I'm just going to write in the second one because it's exactly the same. So V2 in the y direction is equal to V2 times the sine of angle 2, which is 86 times the sine of 20 degrees. All right, so now it's calculator o'clock. We're going to plug in all these numbers. You're going to get really fast at these, hopefully, because you're going to do a lot of them. 120 times the sine of 60 is 104 meters. And I'm going to add something very impressive here. So I'm going to look at this number and think to myself, I'm going to write negative 29.4 meters. Now, this is the interesting part. Why did I write that number as negative? The calculator didn't say negative, did it? So why did I write it negative on my page? So this is actually the tedious and most hard part of this one, and usually where any mistakes happen. Mistakes happen in this chunk. You either get the angle the wrong direction, or you forget a negative in this section. If these four numbers are the correct four numbers, the next steps work every time, and very few people make mistakes in the next step. So the next step, according to my rules, was the combining of them. So I want the total Vx to be V1 in the x direction plus V2 in the x direction, which in this case, the two x's were 60 plus 80.8, which I can do 140.8. And so that's my total x number at this point. The next number is my y number. Vy is equal to V1y plus V2y, and so that's 104. In this case, I'll do it this way. Plus negative 29.4. So I wrote it this way because we're always adding vectors. Adding vectors is what we do. But sometimes those vectors happen to be negative numbers. So I think that's the most real way of writing that. So out of all that, I get 74.6 meters. So it's still overall up, even though there was a subtraction in it. So still, as you can see from this picture, we're going to get a triangle that kind of looks like this. It's 140.8 on one side and 74.6 on that side. Now, at this point, you're going to try to do a little bit of a match. You're going to look and say, this line here, is it close to this line here? And I would say, yeah, it's close to this one. It's going in the same direction. It's in the same quadrant. It's not going this way or anything weird. At least to the level of accuracy that I've drawn this, this is the same. So if the original diagram is like, okay, good, and I think this one is this one, we're probably on the right track. So now that I have this triangle, this is the one I got to figure out. So this is now my Pythagoras step. We're going to do, slide this up a bit just so you guys can see. VR is going to be Vx squared plus Vy squared, all square rooted. So that's going to be x is 140.8 squared plus 74.6 all squared, then all square rooted. That square root looks silly. Let me fix that. Better. And we'll get a number out of that. So at this point in our math, we're not going to do heavy rounding. We're going to keep a bunch of extra significant digits. We only do the significant digits part at the very, very end. So out of all this, get practice in your calculator. I think it's 159.3. 159.3. If you wrote down more digits, that's fine. If you wrote down less, maybe consider adding a few more. 159.3 is probably plenty. That feels good based on our triangle. One side is 140, the other side is almost 80, so 160 is probably feeling pretty good. The next thing to do is find the angle. And the angle is done by doing the tan inverse of the y side divided by the x side. That's ugly, but I think I'll keep it. I'm going to slide up so you guys can see them. Y side is 74, so we're going to do tan minus 1 of 74.6 divided by 140.8. These numbers are not squared, just in case you were squaring them in the last step. You're not squaring them in this step. And this number should spit out a nice angle. It's going to be 27.9, bunch of numbers. And remember, degrees in general, there's 360 degrees in a single circle. 1 degree of angle is incredibly small. 1 decimal place of angle is extremely precise. So you're rarely going to get numbers that are more precise than that. These are the numbers that we need. This is the end of my question. So the final part of all of this, we'll be doing 160 meters at, because I'm really lazy, 28 degrees. And I get to write another important thing, north of east. So, first off, why did I round my final answer to 2 significant digits? Yes. All the original measurements of 120 meters and 86 meters tells me those are 2 significant digit questions. So everything is going to boil down to 2 significant digits in that case. And same with the angles. Basically, angles I tend to ignore a lot. So match them basically. Because we like to use numbers like 30 degrees and 60 degrees, and we tend to ignore all of them. Yes.
Why did you round it up?
For?
160.
Because 59? 59 turns into 60? Oh, and the 3 doesn't round up to 160. The 9 rounds up to 160.
Oh, okay.
Because I'm going to 2 significant digits. To do 3 would be annoying. I would have to break out my scientific notation for 3. That would suck. So 2 is actually slightly more convenient. That's that one. Oh, and the north of east part, right? Whenever we're doing an angle, angles have to be referenced to something. An angle is always a measurement between 2 things. It's 28 degrees between 2 things. In this case, it's 28 degrees from the east up north. So we go from east up to in the north direction. So that's what we mean. North of east. That's kind of what that description is doing. That's, in this case, east, right? And this is the north side there. So it's in the northeast. It's north of east. If we set it the other way around, it goes from the north to the east. That would be east of north, which would be the other side of the triangle, and we don't want that. Okay, that was a whole lot.